All right, more than halfway through the semester, we finally get to the starting point for your high school physics class, pretty much anyway. So today we're going to go through the heart of Newtonian physics, and I'm going to try to show you how interesting and fun it can be when looked at through the lenses of history and philosophy. Which is not to say that the physics part can't be interesting and fun, but it's more fun when you combine these disciplines. So we're looking at some brief excerpts from Newton and DeWitt's chapter on Newton. DeWitt nicely points out that the Principia is a massive work. It's about 600 pages, some of it's very densely argued, but really the heart of it comes down to three laws of motion and a principle of universal gravitation. One of the first things that ought to jump out at you is why not just say there are four laws of motion? And the short answer is that Newton knew that gravity is a very weird notion. One of the things we need to do in this lecture is re-weird it for those of you who have lost a sense of how weird it is. And so Newton is able to introduce the three laws of motion early in the book and explain them pretty thoroughly. We're going to put a little mystery in there, but it's gravity that he really has to argue for in a very distinctive and patient way. So we're going to try to put those pieces together. Newton's first law is well known to most of you. It's the principle of inertia. It's been a long time coming in this class. So in the formulations that most of you are probably most comfortable with, an object at rest tends to remain at rest, while an object in motion tends to continue its straight line, constant speed motion. Tends to is not a perfectly clear notion. The idea here is does in the absence of outside forces. The notion of force is a tricky and crucial notion throughout the Newtonian system. Newton is not the first one to come up with this principle. Descartes got it right. He got there largely via theological argumentation. Galileo came very close to getting it right, but was not clear about the distinction between circular and straight line inertial motion. So part of what Newton had to do is work through Descartes' system, which has a bunch of error and a bunch of insight, and figure out which stuff was worth saving. Newton, so far as we can tell, basically got that part right. So some of it is subtraction rather than addition. So Descartes gets the credit for formulating the principle of inertia correctly. Newton gets the credit for integrating it into a basically empirically adequate conception. We have seen in some detail that inertia is not by any means obvious. You have to move away from the priority of rest within the Aristotelian system. In our experience, practically everything in motion comes to a stop. Now, within the Newtonian framework, we are, as it were, seeing past those patterns in experience and treating uniform motion and rest as essentially identical. Accelerated motion is a different animal. We started looking at that, and we'll have more to say about that as we move forward. Newton's second law these days gets expressed as F equals ma. Force equals mass times acceleration. Very few components of this are as clear as they often feel to people in the 21st century. In Newton's day, it would have been much more common to write this as acceleration equals force over momentum, since it's measurable motion that is generally what's being isolated and measured and tested for. This idea is not that hard to grasp for those of us who have had the groundwork laid for us. The bigger something is, the harder it is to change its state of motion, which is to say, if it's moving, it's harder to stop it. If it's not moving, it's harder to get it going. The more force you apply, the bigger a change in motion you can bring about. But these notions of force, mass, and acceleration are achievements, not given. Hopefully you are now in a position to see that even great minds like Galileo and Descartes had to try to figure out what to measure when you're measuring stuff, what to measure when you're measuring motion. None of this stuff is intuitively obvious. Descartes had roughly bulk, had volume in mind. And as we saw, he thought motion was measured by speed, not velocity. The difference between speed and velocity is velocity includes a direction. So when you redirect something, you change its velocity, but you might not thereby change its speed. With such tools as the calculus, Newton is able to understand mass which is roughly the amount of matter, as the integral of density over volume, for those of you who are comfortable with such notions as integration. But really, maybe force is the trickiest notion to get a handle on for a bunch of reasons, mostly centered around time efficiency. We have not spent as much time on force as we have on the measurement of motion or stuff. So the concept gets brought over from the measure of some kind of activity. But really, it comes into its own as a clear concept in physics only with Newton. Leibniz, Newton's great contemporary, calls force what we would now call kinetic energy, but he is still working much more within the Aristotelian framework than somebody like Newton or even Descartes is. So he sometimes talks about force as if it's within the body, like Buridan's talk of impetus. Impetus, you might remember, is a form, a property of the body by which it is able to move itself. Most of us in the contemporary world don't think there's any such thing as impetus, but the Aristotelian idea is my arm gives to the ball the ability to move itself. Leibniz sometimes talks as if force is in the object. Newton consistently and Leibniz sometimes treats force as part of the explanation of motion. We appeal to forces in order to account for change of motion. But account for can be read ambitiously, as scientific realists do, or unambitiously, as scientific instrumentalists do. So in the kinematic tradition, all you're doing is describing motion, right? We saw that you could read medieval and post-medieval astronomy as just in the business of mathematically describing where celestial objects are going to be. You move that into the terrestrial realm and you're just making predictions, hopefully quantitatively precise predictions about where things are going to be found. That's roughly an instrumentalist conception of force. Force is whatever figures in the mathematical prediction of motion. For realists, though, forces are supposed to be real things in at least some sense of the phrase real thing. And we're causally explaining motion. We're not just mathematically describing it. Newton seems to go both ways on this. His official account of force is that it's exhausted by its mathematical role, which sounds instrumentalist, but under certain pressures to wrestle with gravity, he's going to confront realism as well. All right, Newton's third law: for every action there is an equal and opposite reaction. You're used to memorizing that, and you might think you understand it, but if you haven't fired a gun and you find yourself doing so, you will get a vivid lesson into for every action there is an equal and opposite reaction. We don't always understand the implications of laws of physics we can recite. They're not as commonsensical as high school physics would have you believe. So the recoil on a gun will get your attention if you're not prepared for it. Those three laws are a big deal. The principle of universal gravitation is probably a bigger deal, and it's so familiar to us that we forget how weird it is. Einstein is really going to cure you of that, hopefully in a couple weeks. Newton, initially in the Principia, when he uses universal gravitation, he means the heaviness of everything. Gravity is a word that Aristotle and post-Aristotelians use, but they don't mean what Newton and most Newtonians mean by it, some kind of mysterious pulling force. It means heaviness. It means a tendency of bodies made of earth and earthy things to accelerate towards the center of the universe. Newton has gotten over the earth-centeredness, and so it's the tendency of every heavy body to be accelerated towards every other heavy body all at once. So Newton presents an equation that is directly proportional to the product of the masses. So you multiply the masses of the two objects. We're going to keep it to two objects for the sake of simplicity. And so the force, whatever exactly a force is, goes up with the mass of the objects, and it decreases with the square of the distance between them. So the farther apart two things are, the less gravitational force, again, we're not sure what force means, they will exert on each other. So the masses are in the numerator and get multiplied. The distance is in the denominator and it gets squared. So the force drops off very quickly. I think I've mentioned in the in-class lecture this really interesting story. Some of this was in the air. It's not just that Newton was a singular genius. Halley, Hooke, and Christopher Wren were well on their way towards working out something along the lines of gravity, but they didn't have the mathematical chops. Newton had already done it and just left it sitting on his desk. Brief note for those of you who are physics students. What physics students today do is much easier than what Newton had done and left sitting on his desk. It's relatively easy to derive Kepler's laws as a special case of Newton's laws plus gravitation. What Newton did, much more challenging, derive gravitation from Newton's three laws of motion and Kepler's. If you're not a physics major, don't worry about that. This idea of unification is crucial. It is no exaggeration to say that many people think Newton's Principia is the greatest work of science ever developed. Why is it so great? Because it does the mostest with the leastest. With three laws of motion and a principle of universal gravitation, Newton will explain the tides. He will explain, again, in some sense or another of explain, Kepler's laws of planetary motion. He will show you how to drop large, heavy objects on people you don't like. For just those basically four equations, gravity gets its own special status, Newton is able to approximately explain every motion of everything in the universe. The way he argues for it is crucial. Very slowly in the case of universal gravitation. The laws are presented as almost definitions and as uncontroversial. Newton starts with falling objects, for instance, with projectiles. And he shows, okay, this inverse square law looks like it would fit those phenomena. Then he extends the explanation to the moon, to the other planets, and finally to everything. This is the full demise of the Aristotelian distinction between the sublunar and the superlunar realm. I'm going to stop here and finish in a second part of the lecture that'll be briefer. I don't want to tax your patience too much, so thanks for your time and attention.